The biggest shift here is that world models are starting to behave less like flashy video predictors and more like usable control systems. One line of work shows hallucination isn't random. It can be detected from internal signals and reduced with better data coverage. Another reframes multimodal AI around next state prediction, using Qwen to build a unified world latent space. And in robotics, a new model from Mila and Carnegie Mellon is making imagined rollouts fast and reliable enough for real planning, not just benchmarks. Let's explore the first paper. Hallucination in world models is predictable and preventable. Nicholas Hansen and Xiaolong Wang at UC San Diego show that hallucination in modern world models is not mainly an architectural flaw, but a data coverage problem. It concentrates in low coverage regions of state action space and can be predicted from internal signals. Using their new MMBench2 benchmark of 427 hour 210 task corpus with ground truth actions, rewards, and live simulators, they train a 350M parameter dreamer 4-world model and separate hallucination into 3 failure modes: perceptual errors in the tokenizer, action marginalized transitions in the dynamics model, and scene diverging rollouts. They then introduce 3 label-free predictors: the tokenizer, round-trip residual, flow instability, and interseed variance that correlate strongly with open-loop rollout error, with Spearman Rho around 0.8 across all 3. For mitigation, they reweight sampling to be uniform across tasks rather than frames, which improves rollout fidelity by 0.88 decibels and lowers all 3 normalized hallucination signals. They also use the predictors as curiosity rewards for online data collection, where only 50 real trajectories per task adapt the pre-trained model to entirely unseen environments. On 10 unseen tasks, closed-loop MPC performance rises from 0.276 to 0.325 with curiosity-driven data, compared with 0.118 for a random policy and 0.362 for expert or human data, showing that predictive hallucination signals can be turned directly into data-efficient control improvements. Let's explore the second paper, Orca the World is in Your Mind. Orca, from the Beijing Academy of Artificial Intelligence, reframes multimodal foundation modeling around next state prediction rather than next token, next frame, or next action prediction, using a frozen Qwen 3, 5 VLM backbone to learn a unified world latent space from vision and language. The model is trained with 2 complementary paradigms: unconscious learning over dense video transitions and conscious learning over language-conditioned event transitions plus VQA supervision, using a loss mix of 0.1 for observation-only transition, 0.5 for event-conditioned transition, and 0.4 for VQA. Pre-training uses 12 5K hours of video, 160 M event annotations, and an additional 11 5M VQA data points, though only 1/10 of the inventory is used in this version. With a frozen encoder and lightweight decoders, Orca scales from 0.8B to 4B parameters and improves zero-shot text generation on MV bench, temporal bench, 3 DSR bench, and switch, reaching 51.8 average at 4B. It also tops the real-world price, V01, image prediction benchmark at 59.8 average with a 4B plus 2B readout. In embodied action generation on 5 dual-arm robot tasks, Orca achieves 32.4 overall rule-based score in out-of-distribution settings, outperforming Qwen 3, 5, and approaching 0.5. The engineering stack matters too. Flag scale plus FSDP2, chunked cross-entropy, activation recomputation, and communication prefetching raised throughput from 0.66 to 2.91 samples, SEC, GPU, a 4.4 times speedup over star VLA. Let's explore the third paper, Wever, Better, Faster, Longer, an effective world model for robotic manipulation. Wever, from Arnav Kumar Jain, Yilin Wu, Jesse Fairbrother, Gokul Swamy, and Andrea Bajci, across Mila and Carnegie Mellon University, is a multi-view world model for robotic manipulation that tries to solve fidelity, long horizon consistency, and efficiency at once. It encodes wrist and external camera streams, plus proprioception with a pre-trained Stable Diffusion 3 VAE, predicts future latents with a 3-2 layer, 1536 dimensional transformer trained using flow matching and diffusion forcing, and adds latent reward and critic heads distilled from Robometer to score imagined rollouts without an external VLM judge. Trained at 928 M parameters on Droid for 1 M steps, then fine-tuned on 250 real trajectories from 5 hardware tasks, Weaver outperforms Control World on both in-distribution and OOD manipulation rollouts, including lower Droid exterior FID of 10.2 versus 26.09 at 16 NFE, and lower Droid wrist FED of 90.72 versus 195.37. On real robot tasks, the fine-tuned model reaches RO equals 0.87 correlation between imagined and real success rates for policy evaluation, improves the Pi 0.5 policy's real-world success rate by 38% without additional real interaction, and enables test time planning with 5-10 times faster inference than prior world models, reaching about 20 times lower dynamics latency than Control World in the full planning pipeline. The paper's main contribution is not just better video prediction, but a world model stack that is actually usable for evaluation, policy steering, and online planning on contact-rich manipulation. That's a wrap on today's AI paper highlights. Thanks for watching.